first like to thank the conveners for inviting me. This is my first UNAVCO meeting. I'm a geodynamic modeler, so I'm going to be showing some geodetic data, but I would point people to my collaborators, Falk Amelong, Jeff Reimuller, and Zhang Liu, who have been extremely helpful in helping us in the data side. I also want to thank just my amazing students and postdocs who've been working with me on these problems. A lot of the work I show today will be work that has been conducted by Yan Zhan and Jack Albright. And I also want to recognize the generous support of my funding agencies, NSF's Marine Geology and Geophysics Program, NASA's Earth Surface and Interior, and the National Center for Supercomputing Applications. So we've talked a lot today about the problem with monitoring volcanoes and connecting modelers with data. And one of the things that I'm very interested in as a modeler is how I can best utilize data and observations to better constrain my models and to help them to better understand how the system's evolving. So data, in a sense, gives you that direct observation. We generally have good error estimates, but data tends to be incomplete, and there are gaps in our coverage. And the image I'm showing here, this is from a recent paper with Matt Pritchard, and it illustrates the amazing geophysical data collection effort that his group put on in the Plutons project in Central Andes. And the idea is that you have these great disparate data sets. They're disparate both spatially and temporally, and we want to link them to our geodynamic models. Our models, on the other hand, utilize our understanding of the system state and how a system might evolve. But we generally don't know what our model errors are, and so oftentimes we're trying to depend on models as being perfect when they may be suboptimal. So the goal is to create a model data fusion framework where you take the observations and you link them with the models so that your model can be adjusted. So basically, we're taking our unknown parameters and variables and adjusting them based on our observations so that we can correct our model trajectory. And the models then can also be used to improve our data targets, because they'll let us know where there are gaps in our data collection that we really should focus on. So the goal is to create a forecast correction method using our observations. So in that sense, we have time-forward models. In my case, I generally use finite element models that forecast a system, and then we have observational inputs that help correct that forecast. So the method that we're using in my group is the Ensemble common filter. Now, several people yesterday talked about common filtering approaches, and mostly in the solid earth community, you've heard about the extended common filter and also the extended network inversion filter. The Ensemble common filter is different in that it's using a common filter approach, but it uses a Markov-Chain Monte Carlo suite to generate your models. So this is the framework that we've implemented. At the initial step, we use a Monte Carlo suite to produce n number of ensembles. Those are 4 integrated to produce a forecast ensemble suite. That forecast ensemble is combined with the measured data in the ENKF analysis scheme. And you'll recognize the ENKF analysis is very much a common filter. The main difference is that the covariance matrix from the model in the ENKF scheme is gotten through that Monte Carlo simulation. Finally, that ENKF analysis updates your model state, and then you go back to forward integrate. You can use this in a couple of different ways. You can use it as a static optimization and optimize over and over, but it's also a sequential data assimilation approach. Now, I was inspired to go in this direction through colleagues in the physical oceanography department at Oregon State University. So my first impression of common filtering was looking at large-scale atmospheric land surface climate models. This is also the common filter of choice for NCAR. So it's something that's been used very widely in the climate community, and so there's a really great wealth of publications and things to look towards to utilize this approach. All right, so I'm going to show 2 applications of this approach today. The first application is a hindcast of Okmok's 2008 eruption. So we're going to utilize the very excellent data sets that are available there. Okmok was an ideal place to try this because we have both continuous GPS measurements as well as really good INSAR data. So Okmok erupted in August 2008 after a prolonged period of unrest. This is the OKCE GPS sensor showing the vertical deformation leading up to the 2008 eruption. And it also had INSAR data up to almost just prior to the eruption. So we have pretty good information leading up to the event. In our approach, we're going to be using, for Okmok, a 2D axisymmetric elastic model. I'll get into a little bit more of the different types of models that we can use. For this approach, we're using elastic for computational ease. The elastic model is linear elastic. It's gravitationally loaded. The parameters that we have at our disposal are the geometrical parameters for the shape of the magma chamber and the location, so depth, x, y location. So we're utilizing it in a 3D sense, but it's axisymmetric for computational ease. Our source variable is a pressure change variable. This is assuming that there is a cavity with a pressure boundary condition on it, and the outputs from our model are the displacement, stress, and strain. Our ENKF implementation for OCMOC uses both the INSAR and the GPS data. We're using 300 ensembles in our Monte Carlo approach. The thing that should be noted is there's been a lot of effort in synthetic tests to determine what is the optimal size of the Monte Carlo suite. And it seems that 200 is about the minimum where you can get good convergence. And most of the ensemble tests that the climate modeling community has used usually hover between 300 and 500. I would also point you to some synthetic test papers that I and my graduate student, Anne, have written that have gone through testing this. So at each of the iterations, for each of the time steps, we do iterate on our ENKF for the INSAR data. And this is because INSAR is disparate in time, and we may have several months elapsed between an INSAR observation. Therefore, when we do get an INSAR observation, we iterate on it several times to get better convergence. Because GPS data is much more regular, we do not do an iteration during the GPS time steps. We are binning our data every 10 days, and so we have a total of 203 time steps for our data set leading up to the 2008 eruption. The full computational time for this optimized model is 39 core hours. Now, in terms of the initial values in our Monte Carlo suite, we actually are looking at a very large parameter space. I would also, again, point you to Jan's awesome paper that does synthetic tests to tell you how initial guesses influence the ENKF, and we found that they actually don't influence it too much, and the ENKF usually recovers very well depending on the particulars. Okay, so I'm going to first show you the model fit. On the left here is the GPS data fit for two of the intercaldera sensors, and then one of the sensors, GPS sensors, that's located further away from the deformation signal. And the ENKF is shown in blue, and it's done a really nice job of tracking the deformation signal. On the right, I'm showing two time periods in the INSAR data, again showing the model prediction from ENKF and the residual. Overall, ENKF has done a nice job of reproducing what was observed in the data sets. So what we're really interested in are the parameters. So how is this magma system evolving in time leading up to the eruption? So one of the things that I'm very interested in as a geodynamicist are what are the precursors for eruption, how is eruption triggered, and what does failure look like when you're getting ready to extrude magma from a magma reservoir. So on the top here, we have volume change and the geometrical variables for the magma chamber. So you can see, so we've got time on the x-axis here, and these vertical dashed lines are every time there's an INSAR observation that's been assimilated, and then the entire data stream is shown here in blue. The red vertical line is the eruption in 2008. So leading up to the eruption in 2008, we see a continual increase in the volume of the magma reservoir, which is manifested in an increase in the vertical half width. So it's basically growing laterally. The half height sort of reaches a stability in 2006 and sort of remains constant. Similarly, the position of the magma reservoir remains pretty much constant after 2006. Now, the 0, 0 on these X and Y positions are indicated from the Liu et al. 2010 analytical inversion. And I should also mention that in Zhang Liu's analytical inversion, he found a depth range of 2 to 3 kilometers. So we're seeing a reasonable agreement to the previous static inversion. So the question that we have then is, well, what's happening as we lead up to the eruption? Are there things that we can look at in our model as it's evolving that might indicate to us that the system was trending towards an eruption? So on the top here, I have the calculated pressure change from the magma reservoir leading up to 2008. And you can see that there is quite a bit of variability up until 2005, and then the model sort of remains constant at about 60 megapascals leading forward. I need to make sure that you understand, though, this is just a change in pressure during the time period of our observations. We don't know what the full magnitude of pressurization is because we don't have the information all the way back in time, but it at least tells us what's happened recently or leading up to this eruption. So overpressure as a signal really isn't giving us a lot of indication. So if we look at what's happening at the last time step just prior to the eruption, there's not really an indication in terms of overpressure change that might tell us, okay, there's some sort of precursory signal. On the bottom here, I'm showing percent of models with tensile failure. So tensile failure is something that we can calculate around the reservoir boundary. And what we're looking at are any models that have any elements, even just one, that is in tensile failure. And I'm showing several different tensile strengths here from 0 megapascals to 10 megapascals because there is some disagreement about what the tensile strength might be. Also, it may vary from system to system. One of the things that we notice is that in 2004, during the first major deformation event, there is an increase in the percentage of models that are experiencing tensile failure, and then the increase continues into 2005 where it sort of rolls off. And then you can see as we go into the 2008 eruption, just at the last time step prior to the 2008 eruption, 100% of the models are in tensile failure for 0 to 5 megapascals tensile strengths. So it's actually quite interesting result. On the right here, I'm showing a plot of other things that we can do with this. One of the benefits of the finite element model is that we can calculate stress and strain everywhere, and we can do things like calculate regions of more Coulomb failure, for example. What I've plotted here is more Coulomb failure assuming a cohesion of 0, which not very realistic, but if I give it a cohesion of, say, 5 megapascals, there's no more Coulomb failure, so nothing to show you. In terms of tensile failure, the tensile failure for all of these models, we can track where on the magma chamber boundary tensile failure is occurring, and we pretty much always see it right at the edge of the magma chamber. So I'll zoom in here so you can see. So this is the region of the model space where we're seeing tensile failure. Okay, so our second application is now a forecasting of current unrest. So we can do a lot with hindcasting of previous eruptions. It's nice because we know when the eruption occurred and we can actually dig through the data and the parameters to try to see what sort of precursory signals there might be. We can also use ENKF to provide forecasts when there's sort of near real-time information. So the second example I want to show is from Sierra Negra, Galapagos. The last time Sierra Negra erupted was in 2005 after a prolonged and extensive uplift period. In the period prior to the 2005 eruption, it was recorded over 4.5 meters of uplift. Now again, this is not the full magnitude because we don't have data going all the way back in time, but we do know during this recording period there was over 4.5 meters of uplift. So after the 2005 eruption, Sierra Negra has continued to inflate, and since 2015, INSAR has shown an inflation of over 1.6 meters, and GPS has recorded inflation since the 2005 eruption, which has now shown that it's in excess of the 4.5 meters that it was prior to the 2005 eruption. I am not showing any GPS data today. It's currently being analyzed by colleagues at Penn State, and there's a graduate student working on that, so I don't want to usurp any of his exciting results. So we're just going to focus on Yan's work on the INSAR data since 2015. So our assimilation approach for Sierra Negra is slightly different. We're using a fully 3D elastic model. The reason we're using 3D is it gives us more flexibility with the geometry of the magma chamber, so we can now tilt it and rotate it. We only have 240 ensembles, and that was just a function of the number of cores we had on each of our compute nodes, so we just used 240. We're doing 6 inter-iterations at each ENKF time step, and our total number of time steps is 67. So the compute time for this particular experiment is 1,680 core hours. I think I'm just keeping this in perspective when you're using the finite element approach. Again, we're using a very large parameter space for our initial Monte Carlo suite. So this is our comparison of the fit for the model and the data. So I'm showing 3 of the INSAR time steps, and the ENKF has done a really nice job of reproducing the deformation signal that we see and minimizing the residual. And this is the parameter space. So the illustration on the bottom right here is showing a 3-dimensional look at the magma chamber. So the very first time step where you see all of those magma chambers, that's that entire Monte Carlo ensemble showing all of the different orientations and shapes and sizes. And then up here we have the overpressure evolution for that time period. Again, it's just the time period for the INSAR data. Obviously, if we included the GPS data, it would produce a higher overpressure signal. So the main thing, though, is that the geometry and location of the magma chamber doesn't change much, but the overpressure is continuing to grow during this inflation period. So looking at the failure that's predicted from ENKF, one of the things that's kind of fascinating is that tensile failure is actually coming in pretty rapidly, and we're currently in a state where all of our models that we're running with this data indicate that there's some tensile failure along the magma chamber. Additionally, we're also finding more Coulomb failure in the model space. In this particular model run, we've used a cohesion of 5 megapascals. So the last medium value, so this is just the mean ENKF value for the last model, is showing failure that looks like this. We see more Coulomb failure in the roof, which we've also actually recorded some earthquakes at Sierra Negra, so we do know that there are some faulting episodes occurring. And then you can see the tensile failure in 2 elements along the magma chamber boundary. So one of the cool things that you can do with ENKF is you can take it and forecast into the future. So what I've done here is, or what Yan, my student, has done here, is taken the pressure evolution and projected it forward into time. And what we're looking at is if it continued on this trajectory, what would the model do moving into the future? What you can think about this is if you're doing a weather forecast of a hurricane and trying to determine where the hurricane might hit the coast, you would project those models into the future and try to determine where that might be. But there are some major, major caveats with this type of approach. First of all, again, this is an elastic model. It's homogeneous. We do not think that for the Sierra Negra system that the elastic model really is doing a great job. Given its longevity and size, a temperature-dependent model is far more reasonable. We don't really know which failure criterion might work for Sierra Negra, and maybe a failure criterion for Sierra Negra may not be the appropriate one for another volcano. Every volcano may have a different sort of aspect to that. And finally, this assumed pressure evolution obviously may not be the case. The volcano may stop pressurizing, or we may see a roll-off. So every time a new data point becomes available, we can retune our model and change its trajectory. All right. So in conclusions, at OCMOC, we see that the ENKF does a really nice job of tracking the combined INSAR and GPS to provide model updates in the lead up to the 2008 eruption. We see a change in overpressurization that stabilizes in 2004 at about 60 megapascals, but the magma chamber continues to grow. And so the deformation signal we're seeing is mostly seen in the growth of the magma chamber in terms of the ENKF prediction. And by the last time step prior to the 2008 eruption, we see 100% of our models in tensile failure. At Sierra Negra, we see ENKF is able to track things very well, and the more Coulomb failure that's predicted does match the seismicity that we have been recording at Sierra Negra. But there's some major caveats because we don't really think the elastic formulation is appropriate for Sierra Negra. Given the size and longevity of the reservoir, a temperature-dependent approach is probably much more appropriate. And finally, in terms of future work, one of the really cool things about ENKF is it's model independent. That means you can swap out any model in and out, any model you want into the Monte Carlo suite. Now, I mentioned I'm a geodynamicist, so the simple elastic models is a quick way for us to benchmark the approach to make sure it's working the way we think it should work. We've also developed a lot more sophisticated models where we have things like magma flux, and we are using seafloor geodesy. We're currently funded by Marine Geology and Geophysics at NSF to investigate the eruption cycles at axial caldera. So in those models, we have water columns, we have far-field tectonic stresses. So there are a lot of really cool things that we can do. Also, we're currently partnered with the National Center for Supercomputing Applications, and they've provided us with excellent support, including support to build a fully high-performance computing ENKF method, so the HPC ENKF, which we are running on supercomputers at the NCSA. So we're very excited, and we hope you'll stay tuned to some of the other outcomes from this work. Thank you.
Great talk, Patricia. I was wondering how your model might change if you began to put in some with a local seismicity, because we monitor the volcano with a network of quite a few stations, and it would seem that we should join together on that. And every week we have an event between 3.5 and 4 magnitude. Most of them are VT events, but we've also lately been getting some very long period LPs. So that would maybe imply more solid transfer. But I think I imagine you could put that in your model and it might do a little bit better forecasting.
Yeah.
Secondly, as far as I know from talking to the rock physicist, they tell me that a rock cannot be sustained at 20 MPa. So I just say that because they tell me that. Anyway,
Well,
I like your impressions.
Yeah, well, so on the first point, in terms of seismicity, yes, we are working on new ways to incorporate seismicity into our data assimilation scheme. That's something that we very much want to do because oftentimes seismicity gives you really important indicators, especially of precursors. Because we're tracking both stress and strain, the stress rate can be related directly to seismicity rate, and there are things that we can do, but this is something we're developing right now. In terms of the strength of the rock, that's why we always do the 0, because I think there is some contention about how much strength it might have. So we generally say if it's in any sort of tension at all, we're just going to call it failed. Yeah, Paul?
Yeah, Trish, I was a little confused by the Akmak example. You had the pressure being very stable at the end, and yet the percent of models that reached tensile failure increased. So stress and pressure are proportional in elastic medium. What's causing this to happen?
Well, so you actually mentioned it yourself in your talk, that radius pressure term can't be deconvolved, right? So ENKF has chosen to change the radius rather than change the pressure. So in this point here where we have the radius of that half width changing, so it's expanding, but it's instead of putting that into the pressure term, it's actually changing the geometry of the magma chamber. So whether or not, so I guess you could ask, in this sort of elastic approach, is it pressure that's doing it, or is it simply a lateral movement? And so I would say this is not,
so the
it's
model's
non-unique.
expanding one axis, which is increasing the aspect ratio, which is causing a stress concentration.
Yes,
Okay.
exactly. Jeff?
Yeah, just an interesting observation is that when we're looking at the post-eruptive deformation, which one of my students is doing, what we're getting is actually a model that is, we're using a spheroid model, we're using a simpler approach, but it's wider than it is tall. So it's actually the same geometry that your model is evolving towards. It seems to be what we see after the eruption.
Oh, that's very cool. Andy, did you have a question?
I'm just wondering about if you're running the NCAF models forward towards maybe going towards eruption. I mean, are you concerned about the free surface effect? Because as you're going shallower, right, the stresses of the system really do change when you hit the free surface. Because you go to an environment where you no longer have shear stresses.
So I think you're asking me if I would run this through an eruption, and I wouldn't. Basically, our models stop as soon as we have tensile failure. We say that, okay, we've made it to an eruptive state. We don't currently have any models that track the magma as it's exiting the magma chamber, though Jan has been working on a few different approaches to try to do this. It's not something that we're currently incorporating into our ENCAF.
But I thought
work.
you were suggesting that was something that you could be doing with this.
Oh, I'm sorry if I gave that impression.
Okay.
Okay, we stop it.